I should maybe tell you a few things that are not so old, but maybe a little newer. So here's a newer theorem that says the following. So the dimension of the Grassmannian we know, right? So dimension of the Grassmannian, 3n. Let's focus on 3n. That's 2n minus 9. So that was the table we had earlier. However, but, you know, there exist C1, C2 constants, positive constants, such that n squared is less or equal to the dimension of the Dressian is less or equal to the other one. Okay? So I never know about big O and little o and all that, so I'm going to write it like this. Okay? So the dimension of the Dressian grows quadratically in n for d equals 3, but the dimension of the Grassmannian grows linearly in n. So what this says is that this inclusion is quite dramatic, right? The Dressian is much, much, much larger than the Grassmannian. There are many, many more points in the Dressian than in the Grassmannian. And so this is in a paper with Hermann Jensen. Jensen is the guy who wrote GFAN. Josvik is the guy who wrote Polymake. And then myself. And the paper is called How to Draw Tropical Planes. How to draw tropical planes. And that just appeared on the archive. Okay? Now, how to draw tropical lines, that's trivial. That's lines, right? These are trees. How do you draw them? You know, you draw them from their Plücker coordinates using neighbor joining, right? So there's algorithms that take you from the tropical Plücker coordinates and draw the tree. So the most favorite such algorithm among biologists is called the neighbor joining algorithm. So if you want to draw a two-dimensional plane, a tropical plane, then you need a higher version of neighbor joining. So now we have a phylogenetic sheet, right? We have a two-dimensional tree that sits inside as a tree, and this paper tries to understand what the range of possibilities is, and in particular it looks at those. So these planes that come here, those are the tropicalized planes, and over here we get the tropical planes. Okay? So let me tell you a little bit more about that. So maybe I'll pause for a question. Are there any questions at this point? Let me erase this. Any questions? Okay. So now what I like to do is I like to define linear spaces. So I've defined this morning, I've defined tropicalized linear spaces when the valuation is trivial. I've defined then tropical linear spaces when the valuation is trivial. Those are called matroids. Now I'm going to define linear spaces in general. Okay? So linear spaces. First of all, tropical linear spaces. So a tropicalized plane, is T of I, as before, where I is an ideal of linear forms, but now over a field with a non-trivial valuation. Right? So by a tropicalized plane, I simply mean the tropicalization, the tropical variety coming from an ideal of linear forms. Then we have the following lemma. The circuits still form a tropical basis. They still form a tropical basis for I, but that's now a little more complicated because we have a field with the valuation, right? So Rather than having the ordinary matroids that we had this morning, now we need to talk about valuated matroids. So but still, the circuits form a tropical basis. And the tropicalized linear space, tau of I, is the intersection of n choose d plus 1 at most tropical hyperplanes, namely those coming from the circuits. Right? So if we have a moreover, by the structure theorem, a tropical plane, a higher dimensional tree, is a pure d minus 1 dimensional polyhedral complex in projective space. And moreover, these will be really like trees. They're always contractible. Okay, so if you take a tropicalized linear space, you always get tree-like behavior. You have vanishing homology. Okay, so it's going to be a contractible space. Homotopy groups are 0. Okay. Now there's another theorem which I don't have time to state, and it's still the case that the Grassmannian parametrizes tropicalized linear spaces. So the points on the Grassmannian are in one-to-one correspondence with the tropicalized linear spaces. But now let's define tropical planes and tropical linear spaces in general. And this definition is due to David Speyer. Very proud. So David was a student of mine who just finished a postdoc, and he was hired straight from a postdoc with tenure at the University of Michigan. So I'm a very proud advisor. So anyway, so his definition is that every point goes like this. So every point in the Dressian still defines a tropical plane. I'm going to use that as the definition of tropical plane. So I'm going to do exactly the same that I did early in the matroid case. I'm going to take this property and I'm going to turn it around. I'm going to turn it upside down and make it a definition. So I'm going to start with the point on the Dressian, and it defines a tropical plane of dimension d minus 1 in projective space. And that's the plane defined by this vector. So W is a tropical Plücker coordinate vector, right? So in phylogenetics, these would be triple, these are called phylogenetic diversity in New Zealand, right? So I have for any, 4 or 5 taxa, I have a number. Okay? So L of W is the intersection over all circuits, I0, I1, up to ID, less or equal to n, and then I take the tropical hyperplane given by the circuit. R equals 0 to D, W, I0, IR, take the rth out, ID, tropical product, X, IR. Okay, that's it. So I simply intersect the hyperplanes, the tropical hyperplanes coming from all the circuits, and I use the coefficients of W to be the coefficients. Okay? Now the non-trivial part of this definition is actually a theorem. The theorem says it's still contractible polyhedral complex of the correct dimension. So that's non-trivial. Right? Before, when we have a tropicalized linear space, it follows from the structure theorem for tropical varieties. Now these things are not tropical varieties because they come from non-realizable matroids. In fact, there are many more points on the Dressian than there in the Grassmannian. So therefore, there are lots and lots of these, and they're still contractible, pure, strongly connected of the correct dimension. So that's non-trivial. Now, what can we do with this? A couple of things we can do with this. Let's first, let me show you an example. Let me say a few words about duality. Okay, so there's a very nice duality between the Grassmannian of dn and the Grassmannian n minus dn. Same for the Dressian. So there's the same, duality works for the Dressian. So whenever you have a linear space here, a d-plane, you can map it to an n minus d plane, and then and w star is simply the complementary Plücker vector. So here w is indexed by d element subsets out of an n element set, and here w is indexed by the complementary n minus d element subsets, and you take the same Plücker coordinates. There's no sign change in tropical geometry, right? You just take exactly the same Plücker coordinate vectors, and more geometrically, the duality works like this. So a vector a1 up to an is in the primal plane if and only if the corresponding hyperplane in the dual space a1 x1 plus plus an xn contains the dual plane. Right? That's one way to explain this duality, right? So you have here you have a d-dimensional space. Here you have the complementary space. The vectors here correspond to hyperplanes there, and so then the dual plane is simply the intersection of all hyperplanes corresponding to points on the primal plane. So that works just fine. So let me give you an example that's kind of enlightening. Here's an example. Let's take W to be minus E12 minus E34 minus E56 in R6 choose 2. So this turns out to be in the Grassmannian. So this corresponds, this is the Plücker coordinate vector of a line in projective 5 space. So we run the neighbor joining algorithm to draw this line. Very easy in this case. So it's a line that looks like this, right? So you get a line in P5 that looks like this. And then the dual Plücker vector is the same vector except you're complementing the indices. So it's minus E3456 minus E1256 minus E1234. So that's the corresponding vector that lies in the dual Grassmannian on the other side. And now its linear space, LW star, that's a codimension 2 plane in P5, right? So I have a duality that takes lines in P5 to 3 planes in P5, right? Now that 3 plane has the property, this particular 3 plane is not the intersection of 2 hyperplanes. So here we have a new 2 hyperplanes. So here we have a new phenomenon that's not familiar from ordinary geometry, namely linear spaces in tropical geometry are not generally complete intersections. So in ordinary geometry, a linear space is always, the intersection of hyperplanes, codimension many, but not in tropical geometry. In tropical geometry, we know that this many hyperplanes will be sufficient, but codimension many will not suffice. And let me argue why. It's actually very nice to see in this example. Right? So I have this codimension 2 plane in the complementary space, and I claim I cannot write this in the intersection of 2 hyperplanes. Well, suppose I could. Right? Well, these hyperplanes, they will correspond to points somewhere on this line. Right? So if I had this as an intersection of 2 hyperplanes, H1 and H2, look at the corresponding points. So it turns out, as you take the convex hull, you're going to miss some structure over here. To actually get, this line, what you need, you have to take one more hyperplane somewhere on this branch far out here, and then it's going to be okay. So in this case, turns out the triples of hyperplanes that suffice to intersect to the correct codimension 2 plane corresponds to triples of nodes that should lie on the 3 cherries over there. Okay, so that's an example of a codimension 2 plane complementary to the snowflake tree that is not a complete intersection. Okay, I had too much prepared. This is actually a paper that has lots and lots of pictures. So I invite you to look at this paper and to enjoy the pictures of how one draws a two-dimensional plane. I'm going to skip almost everything. And maybe I will end just with one more theorem. Since I started talking about David Speyer, let me end on David Speyer. So let me state one more theorem. This is Speyer's F-vector theorem. So this tells you about the global combinatorics of a tropical plane. It goes like this. The number of I minus one dimensional faces, I minus one faces, so I'm going to write this projectively, so I'm going to subtract 1 everywhere, of a D minus 1 plane. So the number of I minus 1 faces in a D minus 1 plane in projective n minus 1 space is at most n minus I minus 1 d minus I times 2n minus d minus I, choose I minus 1. Okay. Among these, goes on, so among these, at most, another product, n minus 2I choose d minus I times n minus I choose I minus 1 are bounded. Right? I mean, a tropical variety has bounded faces and unbounded faces, right? Just like, so these are in the trees we have bounded edges corresponding to splits and unbounded pending edges corresponding to the taxa, and these are tight. So these inequalities are tight. And this is a very, very nice theorem. So let me explain a little bit why this is such a nice theorem. So there are a couple reasons. Well, first of all, this what does this say for trees? Okay, so let's say if we have trees. So for trees, we have d equals 2, right? And then I is either 1 or 2, right? So a tree, so if you have a tree, so the most edges and vertices you're going to have is on a trivalent tree, right? Well, if you have n taxa, there's going to be n, I guess, 2, get this right. So we have n vertices. I think that 2n minus 2 vertices and 2n minus 3 and n, sorry, the 2n minus 2 vertices, and then there are n unbounded edges and n minus 3 bounded edges. Okay, so on a tree. That's the special case when d is 2. So if d is 2, we recover this. Okay, so this is for higher dimensional trees, for tropical planes. These are the exact face number bounds. Now, this theorem is actually a very hard theorem, and it's in general still a conjecture. So unfortunately, it's still a conjecture. So Speyer was able to prove this theorem only for tropicalized planes in characteristic 0. We don't have a proof for tropicalized planes in characteristic P, nor do we have a proof in general for tropical planes. Now why is that? It's actually a very hard theorem. So the way Speyer proves this in characteristic 0 is using the K-theory of the Grassmannian. So you really need to understand the K-theory of coherent sheaves on the Grassmannian. And the characteristic 0 comes in because you need Kawamata-Viehweg vanishing. You need vanishing theorems that hold in characteristic 0 to actually get these inequalities straight. We don't know in characteristic P. Now we believe that this holds in general, for tropical linear spaces in general. And the key to this are so-called matroid subdivisions. So you've heard about the word of Laforgue. So Laforgue, who won the Fields Medal for his proof of the Langlands conjecture. So one ingredient there was compactifications of products of PGLNs using matroid subdivisions. So we believe that understanding the matroid subdivisions of matroid polytopes better will ultimately lead to a proof of this in general, and will simplify maybe the characteristic 0 proof. Now the other thing that's very nice is what is the case where these inequalities are tight? There's some beautiful matroid theory. Well, what's a tropical linear space look like? Let me talk philosophy for 2 more minutes, and then we'll stop for lunch. So, well, we talked about locally the link. So we have this piecewise linear space, contractible higher dimensional tree. Locally, at every point, we have a fan. Right? Locally, at every point, we have a fan. And what's the fan? Well, that fan is exactly the fan from the lecture this morning. Like locally, we have a evaluation 0 case that corresponds to a matroid. So a tropical linear space is, a bunch of cells, this many, and each cell is decorated with a matroid, right? Which is the link. That matroid has the link T of M. Right, the link locally in this polyhedral complex is that matroid. So you can think about one way to draw and think about a tropical plane. It's a polyhedral space that's locally decorated by matroids. Another definition, it's a tropical variety of degree 1. So planes, so matroid theory really is tropical projective geometry of degree 1. Now, what are these bounds? Well, this is attained if and only if every matroid in this decoration is series parallel. Okay? So among matroids, sort of the smallest non-trivial matroids that are not direct sums are so-called series parallel matroids. So these are graphic matroids coming from series parallel graphs. They have a Krapos beta invariant as 1. So they're sort of the most, and that's exactly the case of equality. So the case of equality here, where this is sort of tight, the vanishing theorem is tight, is if the linear space everywhere is decorated by series parallel matroids. So I think I'll stop now. Many of you are not combinatorialists. If you do have matroid questions, there's Team Matroid over there. And tomorrow morning, so this afternoon, we'll talk about some problems. We'll meet here at 1 o'clock. And then tomorrow morning, the first lecture is called Morphisms and Secant Varieties. And the second lecture is what is the rank of a matrix? Okay, so before I come to the actual lecture, here's a remark I should have made earlier. So by a pre-variety, a tropical pre-variety is any finite intersection of tropical hypersurfaces. So tropical hypersurfaces are defined by tropical polynomials. Minimum is attained twice. Any finite intersection of those in R to the n, I'm going to call a pre-variety. By a tropical variety, I mean what you actually get from an ideal. So if you actually take an ideal in a polynomial ring or a raw polynomial ring, you get a tropical variety. And there's a little bit of debate right now among the experts. People allow something slightly more general, but maybe for our discussion here, let me use this definition of tropical variety. And then we have the following result. Every variety is a pre-variety, but not conversely. Right? So for instance, if you take 2 lines in the plane in special position, you know, this blue half ray is a pre-variety, but it's not a variety, right? It's not balanced, right? So for instance, a tropical curve in particular has to be balanced. So this blue half ray is a finite intersection of, you know, lines. So so this is a pre-variety but not a variety. And the reason is that every ideal has a finite tropical basis. That says that varieties are in particular pre-varieties. Okay. Okay, I think most everybody is here. So let's come to lecture number 6. So we've done with more than half. You know, 5 out of 10 are done. So this is lecture 6. Grassmannians and spaces of trees. So I'm going to fix a field K with the valuation. I'm going to introduce a polynomial ring and n choose d variables, where n and d are positive integers, d less than n. And the variables I'm going to call p sub I1, I2 up to id, indexed by increasing strings. Now in this ideal, in this ring, there's a special ideal called the Plücker ideal. So the Plücker ideal is the following. So I'm going to call I dn. Plücker ideal I dn is the ideal of relations, algebraic relations, among the d by d minors of a d by n matrix. Okay, so you take the d by d minors of a d by n matrix of unknowns that satisfies some algebraic relations. They generate a prime ideal, right? So it's the prime ideal of algebraic relations among that hold for the d by d minors of any d by n matrix. That's the Plücker ideal. So Plücker is the name of a dead German mathematician. So this ideal is generated by quadratic polynomials. So this is generated by quadrics. And among them, among these quadrics are the so-called three-term Plücker relations. So the three-term Plücker relations are special quadratic relations. I'm going to tell you explicitly. So P I J S times P K L S minus P I K S times P J L S plus P I L S times P J K S, where S is a subset of indices 1 up to n of cardinality d minus 2, and then I, J, K, L are also indices from outside S. Okay? So S is some. Now what is this convention? Well, I define these variables to be indexed by increasing strings, you know. But if they're not increasing, so I just use an alternating convention. So if I write a non-increasing string, for instance 1p132, by convention that's minus p123. So I'm going to use alternating, you know, if I have to permute the indices, I just multiply it by the sign of the permutation. And so when I write IJS, what I mean, I fix an ordering of S. Maybe increasing. Then I take the string I, J, and then the elements of S in this order. Now I might have to, you know, put this in increasing order, and then I have this relation. Okay? So it's understood in this sense. Now, in general, the three-term Plücker relations are not quite enough. They almost generate this ideal, but not quite. They're not quite good enough to generate this ideal. If you want all the generators of this ideal, one thing you can do is you can go to Macaulay 2 which is a computer algebra system. So in Macaulay 2, there's a built-in command called Grassmannian. And since Macaulay 2 and the creators of Macaulay 2 are projective geometry people, you have to say d minus 1, n minus 1. And if you type that and you hit return, you get generators for this ideal. Okay? So there's a built-in command called Grassmannian, d minus 1, n minus 1. You hit return, and you get a list of quadratic generators for this ideal, including the 3-term Plücker relations plus some extra relations. Okay, so let me review a little bit of classical material about the Grassmannian. So we take a few minutes here. So the classical Grassmannian. So just like algebraic, just like homology, this is something all graduate students should have seen. So I'm going to remind you of what the Grassmannian is about. So Grassmann is a dead German mathematician. And the Grassmannian is the following. So we're going to look at the projective variety of this ideal, of I, D, N. So this is a homogeneous prime ideal. So it defines an irreducible projective variety. And it turns out that this variety is smooth. It's actually a manifold. It's a smooth variety. And as a projective variety, it has dimension d times n minus d. Okay? Now, this variety parametrizes. It parametrizes. This variety parametrizes the d-dimensional linear subspaces, vector subspaces of k to the n, an n-dimensional vector space. Now we can, so it's the parameter space for d-dimensional vector subspaces of an n-dimensional vector space, or in projective space of d minus 1-dimensional linear subspaces in an n minus 1-dimensional projective space. So 2-dimensional subspaces in a 4-dimensional space correspond to lines in P3. Now parametrizes has many meanings, actually. So at the most naive meaning, I'm just saying there's every point, there's a one-to-one correspondence, a bijection between the natural bijection between the points on this projective variety and the linear subspaces. But this is actually a correspondence in a functorial sense. So algebraic geometers think about this in a functorial sense. So this has a very precise meaning. But just naively, at the level of sets, let me tell you how this bijection works. So suppose you have such a linear space. I want to show you how this goes. Okay, so suppose you have a d-dimensional linear space. So it's the row space of a d by n matrix, and that's the linear space L. So the corresponding point on the Grassmannian, the corresponding point P, well, is simply the vector of maximal minors of this matrix. Right? So the forward map is obvious. So you take a matrix and a d by n matrix, and you simply make a list of all the n choose d maximal minors of this matrix. These are called the Plücker coordinates. Right? Now, why is this well defined? Well, that's well defined because two different matrices, L and L prime, could have the same row space. But if they have the same row space, they will give you the same up to scaling vector of d by d minors. And that's because if they have the same row space, we get the other matrix by multiplying by an invertible matrix on the left, the d by d matrix on the left, and then that's a global factor that factors out. So this is a well-defined map that takes a linear space and makes the vector of Plücker coordinates. So that's the forward map. So the non-trivial one is the backward map. So if I have a point P on this projective variety, how do I recover the linear space? Well, that goes as follows. So if you have the Plücker coordinate vector, the corresponding linear space is simply the solution set to all the circuits that you read off from the Plücker vector. So our good old friends, the circuits, come in again. So this is the set of all x and k to the n, such that for all indices I0 less than I1 less than ID less than IN, we have the following linear equation: R from 0 to D minus 1 to the R, P I0 up to IR hat ID, and then we multiply with X IR equals 0, and then we close the parentheses. Okay? So you simply, take the Plücker coordinate vector. So IR hat means you erase the ith term, right? So you take indices, a string of length d plus 1. You look at all possible ways of removing one element from the string. You take the alternating sum, and that gives you a linear form. These p's are numbers. They're given scalars. So this gives you a linear form, and then the solutions to these linear forms, that's exactly L. Okay? So you have to check this. So this is a little linear algebra exercise. You start with the linear space, you write down the maximal minors, and then you go back, and you get the same linear space. Okay? Example, so that we're going to be particularly interested in is the d equals 2 case. So here the point, so the Grassmannian, the classical Grassmannian, the variety of IDN. So every point represents a line in projective space over the field. Okay? So that's the end of the review of the classical Grassmannian. So the classical Grassmannian is a very nice manifold. It parametrizes linear spaces, and this is the rule for going back and forth between a linear space and the corresponding Plücker coordinate vector. Okay, so now we're going to define the tropical Grassmannian. So the tropical Grassmannian, we're going to use exactly the same definition. The tropical Grassmannian is going to be, I'm going to call that G or Ger of Dn, and that's by definition the tropical variety of this ideal. Okay, that's the definition of the tropical Grassmannian. So how can you make the tropical Grassmannian? Very simple. You go to Macaulay 2, right, and you say Grassmannian d minus 1 comma n minus d, and out comes the ideal. You take the quadrics in this ideal and you give it to the gentleman there, who will then type it into GFAN, and you hit a button and back comes the tropical Grassmannian. Okay? So that's the tropical Grassmannian. Now what about the tropical Grassmannian? So it's a fan. A priori it's a fan of dimension d times n minus d plus 1 in R choose n, n choose d. Well, really here we took a projective variety, so we have this dimension. Over there, the way I set it up, it's the affine cone. So we have to add one dimension, right? So if I just take the ideal and I type it into GFAN, what comes back is a fan of dimension d times n minus d plus 1. And that's because we have the structure theorem. The structure theorem says we have an irreducible variety, and the tropical variety will be a pure polyhedral fan, strongly connected, of the same dimension. Okay, so that we know. On the other hand, so this fan structure comes from the Grobner fan. So we saw also earlier the tropical variety really is only a set. It's a set, but it always has some fan structure that may or may not be unique, right? We've seen earlier that could be not unique. But here I will mean the fan structure inherited from the Grobner fan of this homogeneous ideal. So that's a well-defined fan structure. Now, there's a fairly large linearity space. So the homogeneity of this. So there's an n-dimensional lineality space. So these are there's an n-dimensional grading. So, or geometrically speaking, we have an n-dimensional torus action on the ambient space that fixes this. So the torus acts by just scaling, we can scale the columns of this matrix, and that gets reflected in the fact that the cones in the Grassmannian have an n-dimensional lineality space, right? So this n-dimensional torus tropicalizes to this n-dimensional space. So therefore, we're going to mod out by this. So we can view, we're going to mod out by the lineality space. And we're going to view the Grassmannian as a pointed fan of dimension this number minus n. Then we're going to draw a sphere, a white beach volleyball around this fan. We're going to intersect. And when we're done with this, we have a polyhedral complex of dimension d times n minus d minus n. So that's the number, that's the dimension. So this one minus that one minus 1 for intersecting with the sphere. Let me give you a little chart, so just that we see, how this grows. So here's d and n, and here's the dimension of the tropical Grassmannian. I'm always going to think about this as a polyhedral complex. Okay, so let's do some examples. So if d is 2, 2, 2, 2, and so on, here we have 3, 3, 3, maybe 4, and so on, right? So n could be 4, 5, 6, 7, maybe here it could be 5, 6, 7, then here the 8 is an interesting case. So then, okay, if we plug into this formula, so here if d is 2 and n is 4, so then this becomes 0. Okay? So the tropical Grassmannian G24 is a zero-dimensional polyhedral complex. Okay? So zero-dimensional complex. Now, I should maybe say, for the algebraic geometers in the audience, this has another name. So this is, in algebraic geometry, this is sometimes called, it's really quite the same as M0 n bar. Okay, so there are no moduli for M04, right? So that's 0. And then we plug in, here we get 1, 2, 3, and so on. Okay, so the Grassmannian of lines in P3 is a zero-dimensional, then one-dimensional, two-dimensional, three-dimensional, and so on. Okay? Then here we get 1, 3, 5, and this is an interesting case. 4, 8 gives 8. So I'm just plugging into this formula, so we get a sense what the dimension of the Grassmannian is like. So I claim that this case, the case of lines, this case is very, very well understood. It's a very, very well-known space. And it's a space that's known not just to the moduli theorists, it's known to the biologists. It's exactly the space of trees that the biologists have studied for a long time. So let me summarize everything we know about the space of trees, G2n, in one theorem. Okay, so this is a theorem that summarizes the situation for d equals 2. First of all, the three-term relations, the three-term Plücker relations, are a tropical basis. For I2n. So for 2n, they form a tropical basis. So in particular, for 2n, they generate the ideal. Right? So for 2n, they generate the ideal. So for the commutative algebraists in the audience, these are the 4x4 sub-Pfaffians of a skew-symmetric n by n matrix. So Pij in this case, are the entries of a skew-symmetric matrix. And Professor Ahn is nodding, right? These are the 4x4 subfaffians of a skew-symmetric matrix. So they generate the ideal, but even better, they form a tropical basis. Now that tropical basis is of course known to the biologist. It's called the 4-point condition. Right? The 4x4 subfaffians tropicalize, as we saw in the high school lecture, they tropicalize to the 4-point condition that's so well known in evolutionary biology. Now as a simplicial complex, the Grassmannian G2n is a simplicial complex. So as a fan, it's a simplicial fan. As a polyhedral complex here, it's a simplicial complex of dimension n minus 4. Okay, so this number here is n minus 4. Okay, so it's a simplicial complex of dimension n minus 4. What are the vertices? Well, the vertices, the number of vertices is 2 to the n minus n minus 1 vertices. The number of facets of maximal cells, maximal simplices, is 1 times 3 times 5 times 7 up to 2n minus 5. So you multiply all the odd positive integers up to 2n minus 5, and that's going to be the number of maximal simplices. So this is going to be the number of facets, n minus 4-dimensional simplices. And it has the homotopy type. It has the homotopy type of a wedge or bouquet of n minus 2 factorial spheres of the correct dimension. Okay? So we know the algebraic topology of this space very, very well. Okay? It's a bouquet of spheres. For combinatorialists, it's a shellable space. It's a shellable simplicial complex, and it's glued from spheres, n minus 2 factorial spheres. And that's it. That's the space of trees. This is the tropical Grassmannian. Okay. What are the vertices? Let me tell you what the vertices are and what the facets are. So a combinatorial model for this space you can build as follows. So the vertices are so-called splits. So by a split, so a split is an unordered pair A comma B of the index set 1 up to n, and this is an unordered pair of non-empty disjoint subsets whose union is everything. So if we have a set, a finite set, by a split I simply mean an unordered partition into 2 sets, both of which are non-empty. Okay? So for instance, in this room, right, there are many splits. So a split could be male-female. That's a split, right? Or people who wear glasses and people who don't wear glasses. Or people of, Korean origin and non-Korean. So these are all splits because A and B are non-empty, and these are unordered splits. Okay? So those are the vertices. So the number of splits of an n-element set is, I think I got this wrong, actually. I think this should be 2 to the n minus 1 minus n minus 1. Okay? That's the number of splits of an n-element set. Question? Pardon me? Oh, the sphere, it's of that dimension, n minus 4. So it's a pure, it's a pure simplicial complex, and so it's gotten by gluing, spheres of that dimension, n minus 4. Okay? Okay, so these are the vertices, are the splits, and let me tell you what the edges are. Okay, so there's this many splits. So for instance, if n is 5, let's say if n is 4, then there should be 3 splits. Let's say if n is 4, then we have 8 minus 5, there are 3 splits. Okay, very good. So 2 vertices form an edge. So if we have two splits, A and B, AB, and A prime, B prime, form an edge. If they're compatible, and compatible can be said as follows. If A is contained in A prime, or if A is contained in B prime, or B is contained in A prime, or B is contained in B prime. Okay? So that's compatibility. So what does compatibility mean? So suppose we have two splits. Okay? Let's say we have two splits. We have the male-female split and the glasses, no glasses split. Right? So, well, all four possible intersections are non-empty. Right? There are males with glasses and there are males without glasses. There are females with glasses and females without glasses. So that's not compatible. So compatible means that at least that one of the four intersections is empty. Right? That's equal to this condition. So if we took the split male-female and pregnant-non-pregnant, that would be compatible splits. Okay? That would be compatible splits. Very good. So those are the edges of the simplicial complex. Now, the Grassmannian is the largest simplicial complex having those edges. It's a so-called flag complex. Right? So now the Grassmannian, G2n as a simplicial complex, is the corresponding, what combinatorialists call the flag complex. Right? So what this means is a collection of splits forms a simplex if and only if any two are compatible. Right? So we're defining simplices by pairwise compatibility, and this is a simplicial complex, and this is precisely the simplicial complex we get here. So let me show you some examples. Well, first, so the silly example is n equals 4, but let's actually do this. So for n equals 4, there are precisely, three splits. I'm sorry, I should have said that. So, yeah, I want A and B to have cardinality at least 2. I don't want people to be lonely. I mean, nobody is supposed to be lonely in their group. So A and B supposed to have cardinality at least 2. Okay, so to make a split, there shouldn't be like a single male or a single female. That's not allowed. Okay, so A and B have to have cardinality at least 2. So on a 4-element set, there are 3 splits. There's the 1, 2, 3, 4 splits, and then 1, 3, and 2, 4, and then there's 1, 4, 2, 3. So those are the vertices. Okay, what about the edges? Well, we have to connect 2 splits if they're compatible, but they're not compatible. Right? So no 2 are compatible. So that's it. Okay, so therefore what I've drawn is a 0-dimensional simplicial complex. It's a 0-dimensional simplicial complex. It has 3 vertices. It has 3 facets. 2n minus 5 is 3. And it has the homotopy type of the bouquet of 2 0-dimensional spheres. Right? So, indeed, right? So this space is gotten by gluing 2 0-dimensional spheres. It's a silly example, but it's good to start with something silly, right? So let's do the next case. Let's do n equals 5. So the GFAN expert, of course, now is ready to go, right? So there are 5, Plücker relations. The Plücker relations are P12, P34 minus P13, P24 plus P14, P23. And P12, P35, and so on, right? There are 5 Plücker relations. So we can type them in, right? Then we type them into GFAN. And lo and behold, we're going to get a graph, right? So now we're supposed to get a 1-dimensional simplicial complex. So we're going to get a graph, And the graph is the Petersen graph. Looks like this. I'm going to explain the notation in a moment. One, 3, 1, 4, 2, 4. So these are the 10 2-element subsets of a 5-element set. I'm going to make a graph by connecting 2 if they're disjoint. Right? So I'm connecting disjoint pairs. Okay, so this is the Petersen graph. Now each of these nodes I'm going to identify with the split of a 5-element set, right? Because if I have a group of 5 people, well, every split will be 2 people and 3 people, right? So this is the split where 3 and 4 wear glasses and 1, 2, and 5 don't wear glasses. And this is, some other split, right? 1 and 5 are female and 2 and 3 and 4. So I'm just listing these pairs, but each of these pairs represents a split. There are 10 splits. And then these edges are exactly compatibility of splits. That's it. So that's the Grassmannian. Okay. The last homework, which we'll discuss today over beer, is to draw the next one. Right. So this one is n equals 5. You can see this has the homotopy type of the wedge of 6 one-dimensional spheres. And today over beer, we're going to draw a 3-dimensional simplicial complex that will have the homotopy type of 24, the wedge of 24 two-dimensional spheres, and so on. Okay, so that's over beer. That's the last question on the homework. But of course, you can just also type in the Pfaffians, the 4x4 Pfaffians of a skew symmetric. You don't even have to type. Okay, you go to Macaulay 2. Okay, and so to do this last homework, you go to Macaulay 2. You say Grassmannian 1, 5. You get some stuff. You cut and paste that into GFAN, you hit the button, and then you've done the problem. Right? That's another way to do it. Okay, so that's the tropical Grassmannian. Now, what about those trees? So I claim that this combinatorial data corresponds to trees. So the simplices are the simplices in the Grassmannian 2n. Let me say one more thing about the topology. I mean, you can go much further, right? I mean, you can calculate the homology groups. Now, whenever you have a space and you have a highly symmetric space, you don't just calculate homology, because you also want the homology group together with the representation of the symmetric group, right? The symmetric group acts on this. We're permuting, 1 up to n. Everything is completely symmetric. So really, you don't want just the homology groups. You want to have the characters of the irreducible Sn modules that sit inside there, right? So whenever you have a group action, you want the homology together with the group action, and everything is known. About this space, any question you might have, the answer is known. Okay? About this particular space. So the simplices in the Grassmannian correspond to so-called trees, phylogenetic trees. The trees with n labeled leaves the n-labeled leaves. And, well, of course, those trees, they are going to be tropical lines in TP n-1, right? After all, the Grassmannian is supposed to parametrize linear spaces, right? If this Grassmannian parametrizes linear spaces, and if linear spaces are trees, well, then it better be the space of trees. So that's good. And the 4-point condition is exactly the defining equations. What about the splits? Well, suppose let me illustrate it in this picture. Okay? So suppose I'm at this node. So on this simplex, there's going to be a tree that looks like this. It has one internal edge, And it has 3, and 4 on this side, and 1, 2, 5 on that side. Okay? And this internal edge corresponds to the split. So here are the mammals, and here are the fishes, whatever. I mean, shark and tuna or something. And here's you and me and monkey, right? Or something. And then this split, separates the clades. Now, as you go here, you have another one. As you go here, this non-trivalent node will bifurcate, right? And now you have 2 splits, right? You have 3, 4 here, and then you have 1, 5 here, and 2 there, right? So you can see now there are 2 splits. There's this split and that split. And at every tree, so trees are combinatorially in bijection with compatible collections of splits, and so being to fit together on a tree, and so on, right? So here we have these splits, and these guys in this picture, they correspond to so-called cherries. So cherries are 2 leaves that are together at the end. So you can decorate this picture. So over here, you go 3, 4, 5, 1, 2, and you can decorate this. So the Peterson graph, the edges correspond to the 15 trivalent trees on 5 taxa, and then the vertices correspond to these degenerate trees, and so on. And tonight, over beer and pizza, we're going to draw the same picture for 6 taxa. So that's how it goes. Okay, so that's very, very well known. Everything is known. I'm exaggerating, but basically everything that you might want to ask about this space is known for d equals 2. And therefore, we're going to look at higher d. And much less is known for higher d. Let's see what we can do for higher d. So now let's say d is greater or equal to 3. Now, what should this be? Right? They should be spaces of higher dimensional trees. Right? For d equals 2, right, we have trees are the same as lines in projective space. The tropical Plücker coordinates up to sign are the pairwise distances, right? So tree metrics are exactly the same as lines in tropical projective space. So if that is so, higher dimensional trees should be higher dimensional linear spaces. And their Plücker coordinates should be higher distances, higher notions of distances. So let's make this precise. Let me do one more definition. So I'm going to define another space. So the Grassmannian ger dn sits inside another space der dn, which I call the so-called Dressian. And the Dressian, by definition, is the pre-variety, tropical pre-variety defined by the 3-term Plücker relations. Okay, so for d equals 2, they are the same, right? Because the 3-term relations form a tropical basis. But for higher d, they're not a tropical basis. And so the pre-variety could be larger. Now Andreas Dress, is a alive German mathematician, very much alive. So he is a quite distinguished algebraist who turned to computational biology much before the rest of us years ago, and he is now the director of a joint German-Chinese computational biology institute in Shanghai. So he looked at these structures under a different name, and we found it quite appropriate to call this pre-variety the Dressian. So the Grassmannian is the variety, the Dressian is the pre-variety defined by the 3-term Plücker relations. So in Dress's language, this is the set of matroid valuations, valuated matroids. In general, these two are not the same. So here's an example. Let me show an example that they're not the same. So I claim the Grassmannian 3,7 is not the same as the Dressian 3,7. Let me assume for a moment that my field has characteristic different from 2. Okay, so K is now a field characteristic 0. Okay, so let's take W to be the following vector: minus E1 1, 4 minus E 2, 5 minus E 3, 4, 6, and then, so I'm going to take the indices cyclic, 4, 5, 7, 5, 6, 1, 6, 7, 2, and finally 7, 1, 3. Okay? So I'm going to take this negative linear combination of standard basis vectors in R7 choose 3. So the ambient space has 7 choose 3 standard basis vector. I'm going to take this particular configuration, and this configuration corresponds to the so-called Fano plane. So the Fano plane is a matroid that looks like this. So I have a rank 3 matroid on 7 elements, and the labeling is 1, 2, 4, 3, 6, 7, 5. So these are simply the indices of the 3-element circuits. In fact, here all the circuits are 3 elements. So these are the indices labeling the circuits in the Fano plane, and that's my W. Now I'd like to argue that this W is in the difference. It lies in the Dressian, but it doesn't lie in the Grassmannian. Let me prove both to you, okay, just by hand waving. So why does it lie in the Dressian? Well, I claim it's compatible with all 3-term Plücker relations, and that's because it's a matroid. So there's another axiom system. So I gave you the circuit axioms, but there's also a basis exchange axiom. Team matroid over there answers all your questions. Okay. So, and since this is a matroid, it is actually in the Dressian. So basically, being supported on a matroid is equivalent to being contained in the Dressian. It's not in the Grassmannian because it's not realizable over a field of characteristics 0. You cannot draw 7 points in the plane such that they have exactly this collinearities. Suppose you don't believe me. Let's prove it from first principle. So how can we show that this W is not in the Grassmannian? Well, let's go back to the definition. By definition, the Grassmannian is the tropical variety of the Plücker ideal. So I have to prove to you that the initial ideal, so not to be in this tropical variety, means the initial ideal of the Plücker ideal with respect to that weight vector contains a monomial. Oh, fair enough, right? You go to Macaulay 2, you type Grassmannian 2, 6. You say, give me the initial ideal with respect to these weights. Comes back. Then you say, do you contain a monomial? And yeah, contains a monomial. That's the proof. Okay? That's how you prove that something is not in a tropical variety. You find a monomial in the initial ideal. But it's actually a quite subtle situation. So what Macaulay comes back with, there's going to be some big monomial in P's, so there's a big monomial in P's, and then there's a lot of stuff, but the coefficient, it's going to be an integer, it has going to integer coefficients, but the coefficient of the leading term will be 2. So it's 2 times a monomial in P plus lots and lots of stuff. And in characteristic 0, 2 is not 0. Right? So there's a monomial in the ideal, but in characteristic 2, it wouldn't work. Okay? So you're going to see this when you do this calculation. Okay, so we've defined the Grassmannian, we've defined the Dressian. So what can we say about the Dressian and the Grassmannian?